Hi everyone, Mr. Lee here. In this video, we're going to go over the QQT problem that we did last Friday, and this deals with rotational momentum, rotational everything, right? Kinematics and torque and all that. So to give you a refresher on the situation, we have two pulleys. We have pulley A. Let me see if I can make a better circle. Good. We have pulley A, and pulley A is a solid disc, okay? And we have pulley B. And pulley B is a concentrated ring. So this here we have a disc system, and here we have a ring system. And both of these pulleys are being pulled by a spring scale, and that spring scale exerts a force down, like so. Okay, and here's what we know about the situation. So one of the things that I've been trying to emphasize is as you are reading these problems, it's important to identify the variables that they give you. Okay, so I'm going to make a list of those variables. We know that, so we'll say for A and B. Okay, we know that the radius for A is equal to the radius for B. We know that the total mass, okay, so the total mass for A is equal to the total mass for B. Now I'm going to have a little caveat here, okay, because this is not what we actually want to know in order to solve this problem. So I'm going to do a little caveat there in a little bit. We know that the force for A that is being exerted, so both of these spring scales are equal, okay, and so what the problem is looking for is, well, we know that they both will make one full rotation. So we know that their theta final for both, for A, is equal to each other because they'll both make one full rotation. But the question is asking, what about the time? Okay, what about the time? The time for that rotation, all right? What is it? Which one will rotate faster? So before we do that, there's one last one. The initial velocity, excuse me, that should be omega A initial is equal to omega B initial, and they both equal to 0 radians per second. All right, so let's go back to this this mass idea here. So this is one of those fundamental concepts that you needed in order to solve for this problem, and that is, even though A and B have the same mass, the mass for B is concentrated on the outside edge. And so the part that's actually rotating, okay, the furthest most point, and that's the part that we want to focus on because that's where the force is being acted on, all right? So the furthest most point, I'll do this in a different color. So the furthest most point right there, okay, this one has a higher concentration of mass at furthest rotating point. Okay, compared to B, because the mass is spread throughout the entire pulley, okay, because the mass is spread throughout the entire pulley at the same radii r away, okay, and we want to look at that radius r because that's where the force is acting on, okay, we have a smaller concentration of mass. Okay. All right. Now this is important. I'm going to be working with both the translational version and the rotational version of this side by side because I find that the rotational version, because it has like Greek letters and letters that we're not really used to, it might be a little bit complicated. But this is what we know: the ability for an object to go against the object at rest stays at rest, right? So that's called the law of inertia. To go against that, and so it's the ability for this object to be accelerated, and that actually comes from Newton's second law. So if a force is exerted on an object, that object will accelerate. All right, let's say that one more time. When a force is exerted on an object, that object will accelerate. So we know that for both situations, for A and B, we said that they had the same force. Okay, so right here, they had the same force. However, the force that is exerted for B has a greater mass. All right, so we'll do this over here. For B, it has a greater mass that is located on the outside edge. Therefore, it will accelerate less. All right, so this is for B. I'll do one for A. So for A, we can say that on the rotating, the furthest r away where the force is actually being acted on, there's a less mass here. Therefore, the object will accelerate more. Okay. Now remember, acceleration isn't how fast it's moving. It is how much the velocity is changing. So A will go from rest to moving at a greater rate. So if we take a look at question A, it says, which one will complete a full revolution the quickest? Now because A has, why did I put two S's for has? I don't know. Has less rotational inertia I. Okay, we can say that like this. Boom. Okay, because object A has less rotational inertia than object B, it will rotate one full revolution, aka 2 pi, okay, at a lesser time. I don't know. It'll go around quicker. Okay, because it's accelerating more. It'll get faster and faster and faster at a quicker rate. All right, so we can say that. All right, so for B, it says derive a equation for time t it takes for pulley A to complete one full revolution. Let IA be the pulley's rotational inertia. Express your answer in terms of F of S, I sub A, NP, RP, and physical constants as appropriate. All right, now part B, it threw us in for a doozy. Okay, it was pretty tough. All right, and I even had students ask me at the end of class, is this even possible? Is this even doable? And the answer is yes. And the answer is yes because of all the tiny little clues that they left us. All right, so here's what we know. We know that there was a force and there was a radius. Okay, 4 times radius, this gives us torque. All right, so if you go to your equation sheet, this isn't the only equation for torque. We also have I alpha. Now, at this moment, what I want to do is I want to emphasize all of the variables that they gave us. Okay, so within the question itself, there's a lot of tiny clues. So for example, there was F of S. Okay, they told us to use F of S, I sub A, mass of the pulley, R sub P. Okay, so they gave us all of this, and they also said we can use any physical constants. And so what that means, physical constants is like pi, G, capital G, which doesn't really apply here because that's like planetary stuff. But these two can apply for our situation here. So in order to solve for this, okay, I take a look at the list of variables that they gave us, okay, and I got to think to myself, all right, so if I'm given these variables, right, and I also know a couple of things. It makes one full revolution, okay, so that they're basically telling us theta final, and they told us what theta initial is, right? Theta initial is 0, and theta final is 2 pi, okay? They told us this within the prompt. They also told us a myriad of other things. They told us that it started from rest, okay? Omega initial is 0, all right? So they also gave us this, so what I boxed in here, I'm gonna highlight that in a different color. Let's highlight that in blue, okay? What they gave us here was within the intro part, okay? And this right here, this is within the problem. So my strategy for you here is you take a look at the variables that they gave you and you try to find the correct equations so that you can solve for the answer itself. And so what it's asking for us is we want to find t time, okay? What is the time t, all right? So we're trying to solve for t. So if you go to your equation sheet and you go to the part that gives us all the equations for the rotational kinematics stuff, right? Because time is only there, you should be able to find out that we have theta final is equal to theta initial plus omega initial times time plus 1/2 alpha t squared. Okay, that is, well, that and the other equations are the only ones, the other kinematic equations, where t is actually represented. And we need to use that one because that's what we're solving for. We're solving for time, gosh darn it. Okay, we're looking for that. And so we have to use this equation. All right, now here we have to use the variables that they gave us. Notice they don't give us theta. They said we can't use theta. And so we don't have to because we can use 2 pi instead because 2 pi are constants. Number 2 is a constant and pi is a constant, all right? Now, what about theta initial? We started at position 0, and so that is just 0, all right? And what about initial velocity? Well, it started from rest, so that's also 0. Okay. All right, and then we have 1/2 alpha t squared. All right, so I'm gonna clean this up a little bit. 2 pi is equal to 1/2 alpha t squared. Now from here, we have to check ourselves. Can we even use this equation? And the answer is no. And the answer is no because we have variables that we cannot use. So I will highlight the variables that we can use. And then that will help us identify which ones that we have to fix. 2 is a constant, check. Pi is a constant, check. 1/2 is a constant, check. Alpha, can't use alpha. They told us we can't use alpha. Okay. Can we have t? Yes, we can have t because that's what we're solving for. Check. All right. So right now at this moment, here's strategy time. Right. What is alpha? How can we find alpha? And so I take a look at my list of available variables. I'm like, oh, I'm kind of scratching my head. Oh no, like time's running out. And then at this point, hopefully you can get to the idea that force times the radius gives you torque. All right, so we have torque is equal to force times the radius. Okay, and this also equals I alpha. All right, so here's what's cool. When we take a look at this equation and we take a look at the equations that are A-OK, I'm going to put a check mark next to it. Can we use torque? No, we can't use torque. Can we use force? Yes. Can we use radius? Yes. Can we use I? Yes. Can we use alpha? No. So we can't use 2 out of the 5 variables. So all that means, okay, is you need to be able to rearrange this equation so that we're only using the variables required. Watch how we do that. F times R is equal to I alpha. All right. So we want to substitute alpha into this equation over here. So we can say that alpha is F times R divided by I. So here I'm putting this bad boy in right there. So we get is equal to 1/2. I'm gonna put this in parentheses. FRIA. I want to use their variable system, so I'm gonna fix that up. There we go. Okay, and then we have t squared. Are we finished yet? Nah, we're not finished yet because we have to solve for t time. All right, I'm going to multiply both sides by 2 to get rid of this 1/2. So 2 times 2 pi gives us 4 pi. Okay, and then we have fs rpia. Okay, all parentheses, that is equal to t squared. We're not done yet. We're trying to solve for t time. Okay, and so I'm going to divide both sides by this big factor here. So we get 4 pi divided by 4s rp is equal to ia is equal to t squared. Are we done yet? No, because we got to actually take the square root of both sides. Oh boy. Okay, and then we get t is equal to the square root. I'm going to make this nice and big of 4 pi all divided by 4s rp IA. Okay. All right. Now here we can clean this up a little bit using our math magic, and yeah, I mean we could just like go from there, right? Okay. That should be FS, not 4S. FS. I'm gonna bold that correction. That should be FS. Excuse me. FS. Okay, so if I were to clean this up, I would get the square root of 4 pi I sub a all divided by f of s r p. So all I did here was I moved this denominator up there into the numerator. Okay, and we get that as your answer. All right, so I do want to spend a little bit more time on this question to give you the list of things to do. All right, now these steps are always going to be the same. 1, identify what you have to solve for. Have to solve for. Boom. All right, so in this case it was t. And 2, identify the given variables. Now this is important because if you remember back when we did the kinematics unit and we created a chart and we filled in the chart, and what I mean by that chart is we did like XO, XF, VO, VF, A, T, right? So these were all the given variables and you had to like, put in the numbers. And so it's kind of like that where when the problem gives you what to use, they're giving you their chart, right? They're telling you you have to find an equation that can use these variables. So you have to identify the given variables, all right? And 3, you have to find the equation, okay, with the missing variable, and that missing variable is what you're solving for in number 1, okay, and then from there you just have to manipulate the equation. Okay, until you find the missing variable. Now, for those of you thinking this, I can't do this. It was way too impossible. I want to tell you something here. This problem is extremely similar to every single practice problem that we have done. The only thing that was different this time was they didn't give you any numbers. Okay, so this is a skill that we've been practicing over and over and over again. It's just a word problem, but instead of giving you numbers, they just give you variables. And so all you're doing is you're solving in variable form without any numbers. Okay, so keep that in mind as you move forward and as you practice the different QQTs, where they ask you to create the different equations. All right, next, part B2. Part B2 is asking, is your answer to part B1 consistent with your answer to part A? Ooh, this is cool. And so here's my answer for B1, and we said that for our answer for part A, we said that as I decreases, we said that I and T are directly proportional. And if we take a look at this equation here, I is in the numerator, T is in the numerator, and so yes, they are both directly proportional, and they're also on the opposite sides of the equation. All right, next we have block C. So this is part C. And this time we have pulley A. And then remember, pulley A was that disc, and it's being pulled down by a constant weight with mass M. And for C, all they're asking is what's happening with the net torque and angular momentum. Now, the key here is just find the equation. Okay, so if it's talking about net torque, all you have to do was find the torque equation. Torque is force times radius. Okay, the force, is this block changing? No, that's constant. Is this radius changing? No, that's constant. Therefore, your torque is constant. All right, now what about angular momentum? All right, so we have angular momentum. Okay, so all you had to do was find the equation for angular momentum. All right, so on the equation sheet, you'll be given 2. L is equal to I omega. All right, so you got to think to yourself, all right, so if it starts from rest, okay, and later on it gains velocity because it's moving, okay, so velocity increases, therefore your momentum increases. So yes, it's increasing. Now another way you could look at this is you could take a look at the change in momentum equation, all right, which is equal to torque times the change in time, which is equal to I omega final minus omega initial. Okay, and we know because there is a torque, yes, exclamation point, yes, yes, that means there is a change in momentum, yes, yes. I don't know why those were upward arrows, right? Okay, and as for the last one is part D. Now part D, quite a doozy, if I do say so myself. We have a spiraling, I should have spiraled that the other way. Okay, we have a spiral system, and the object, as it falls, this thing unravels. Okay, as this thing falls, it unravels. Oops, I drew that incorrectly. Excuse me. Whee. Whoop, there we go. Okay, and so right here, R is decreasing. All right, so that was the situation of the problem. And if you take a look at D, they're asking basically the same thing, right? Net torque, is it increasing, decreasing, or not changing? Well, you just got to take a look. Find the equation. Torque is force times radius. The radius is decreasing, therefore your torque is decreasing, and your force remains constant because that is the mass of the block. Okay, I'm going to label that as W. Okay, so they're both decreasing. Rotational kinetic energy. Okay, so for this one, just find the equation for rotational kinetic energy. K rot is 1/2 I omega squared. Okay, so it's speeding up. So this is getting faster, therefore K rotational is also increasing. Another way you could look at it is work is equal to the change in energy. Okay, and we know work is force times the displacement. Okay, so this force is acting on the system and is increasing and increasing, increasing. Therefore, there is a change in energy. Therefore, there is work being done to the system. All right, so there's two ways that you could have approached it. All right, so that was the QQT. I do have to say that for this one, definitely part B was the most difficult part because it's just something that we've seen before, right? It's just solving a problem, but with a twist. All right, now for parts A, C, and D, I do have to say that A was mostly like a conceptual part, except, you know, if you actually knew the concept and all you had to do was find the correct equation. And same goes for C and D. You just got to find the right equation. Okay, the equation is your roadmap. Find the equation, find how the variables work off of each other, and then you will be golden. Students of mine, I will see you next time. We will be doing more of these problems. I'll see you later. Bye-bye.